Swayam Prabha. Digital India. Educated India.
In the previous lecture, we saw how the Reynolds flow model provides the boundary conditions for the boundary layer flow model. And as you recall, the Reynolds flow model is nothing but N W equal to G times B. So, today our interest is to find out how to evaluate G and B, so that we can safely assume apply Reynolds flow model for practical problem solving. So, I will first consider the laminar boundary layers, then turbulent boundary layers, and then give the overall procedure for calculating the mass transfer rate N W. So, now consider laminar boundary layer with T W constant, that is constant wall temperature, and with suction and blowing, but without viscous dissipation. Now, for this case, you will recall from our lectures on laminar boundary layers that the similarity solution for constant properties is nu x divided by R e x to the half equal to minus theta prime 0 as a function of m, the pressure gradient parameter, Prandtl number, and the suction and blowing parameter B f. And B f, as you will recall, is nothing but V w by u infinity R e x to the half, and the Nusselt number is given as h x x by k x dt dy at the wall divided by T infinity minus T w. This corresponds to, in our general mass transfer problem, this corresponds to psi equal to T, and because this is a single phase fluid, the same fluid being blown or sucked through the boundary layer, we would have omega k equal to 1. In other words, there is no mass transfer driven by concentration gradient. And if we assume constant specific heats in all states, then this simply represents G gamma psi by d psi by dy at the wall, psi infinity minus psi wall, and therefore, the Sherwood number G x x by gamma psi would be equal to x d psi by dy at the wall, psi divided by psi infinity minus wall, equal to nu x. So, there is a clear correspondence between heat transfer and the corresponding mass transfer, where presently the variable T is interpreted in terms of mass transfer G, mass transfer coefficient G. Now, this will enable us to convert all the data that we had computed for the heat transfer case to the Sherwood, converted Nusselt numbers to Sherwood numbers, and also convert B f to the corresponding B psi for the general mass transfer variable. So, we can interpret B f, for example, which is V w divided by u infinity R e x to the half. V w is nothing but N w divided by rho, and therefore, N w by rho infinity R e x to the half, and N w is G times B psi divided by rho u infinity R e x to the half. I am going to now multiply this with x and divide by x, as well as multiply by gamma psi and divide by gamma psi. Then you will see this will become G x by gamma psi into gamma psi divided by mu into mu by rho u infinity x into R e x to the half B psi. But rho u infinity x divided by mu is 1 over Reynolds number, and therefore, this will become equal to, this is Sherwood number, this is the gamma psi by mu, Rex to the minus half into B psi. So, Bf is equivalent to B psi with this multiplier, and this shows that the driving force B psi is proportional to Bf, and hence the similarity solution to the psi equation can be interpreted as a Sherwood number divided by Rex to the half as a function of m mu by gamma psi, which may be taken as Schmidt number, and B psi, the driving force based on conserved property psi. M again here is the pressure gradient parameter, of course, but the Prandtl number is replaced by mu by gamma psi, which is the Schmidt number, and the Bf is replaced by B psi, which is the driving force for conserved property psi. So, using the last relation, the constant property heat transfer solutions can be converted to mass transfer solutions. So, consider for example, the case of Bf equal to minus 2, m equal to 0 and Prandtl equal to mu by gamma h equal to 1. These were given in lecture numbers 9 and in slide 10. And for this particular case, NUX Rex to the minus half equal to minus theta prime 0 was read as was calculated as 2.1, and that would equal Sherwood x into Rex to the half. So, what will be B psi? As you can see from the previous slide, B psi would be Bf multiplied divided by SHX Rex to the half into mu by psi, and that is what I have done. So, mu by psi minus theta prime 0 into Bf, and this is 1 over 2.1 into Bf, which was minus 0.2. So, this will become, and mu by gamma psi here is 1. So, that will be minus 0.9524. So, I have this would be the exact conversion when mu by gamma h will be equal to mu by gamma psi. But if, for example, if I now take different Schmidt numbers, so next slide shows convergence for mu over gamma psi equal to 0.7 and m equal to 0. So, that is what I am going to do now. Remember here mu by gamma psi is same as mu by gamma h 1. So, B psi would be whereas Bf is minus 2, B psi is minus 0.9524. So, let us see what the conversions are on the next slide. So, here are the conversions. Bf values are given here. These represent the suction, negative values represent suction, the positive values represent blowing. 0 of course means no suction or blowing, and these were the values computed in our lecture 9, minus theta prime 0 equal to 1.52, 0.872, 0.57 and so on and so forth. The higher the suction, the greater was the Nusselt number, as you can recall. Now, correspondingly, B psi, which is equal to SC Schmidt number into Bf divided by minus theta prime 0 would become minus 0.921, and I am now taking mu by gamma psi equal to 0.7, then B psi would assume all these values. Notice that for Bf equal to 0.5, B psi actually becomes equal to 6.77 because theta prime 0 is very, very small. We can now calculate G over G star. Essentially, G star is 0.291. So, G over G star would be minus theta prime 0 divided by 0.291. So, this 5.223 is simply 1.52 divided by 0.291. 0.872 divided by 0.291 is 3. 0.57 by 0.291 is 1.959, and 0.429 divided by 0.291 is 1.474. 1, and then likewise here 0.57, 0.368 and so on and so forth. The most important thing to note is that when Bf is very large, both on the negative side or positive side, and likewise B psi is very large, G over G star does not at all equate to ln 1 plus B psi by B psi. As you can see, this is 5.223, whereas this is 2.77, large variation. Same thing at minus 1, same thing as minus 0.5. But for minus 2.5 and bigger values between say 0 and 1, perhaps these two values will come much more close to each other. Similarly, on the blowing side, 0.57 and 0.683 are reasonably close, but 0.368 and 0.5 are widely apart, and 0.1776 and 0.303 are again very widely apart. So, we can tentatively conclude that for minus 0.25 B psi, G over G star is approximately equal to ln 1 plus B psi by B psi. But for large mass transfer rates, that is for large driving forces, the Reynolds flux model is not at all satisfactory, and for these condition cases, numerical solutions are desirable. These observations also apply to other values of m and SC. So, by and large, the whole idea of relating G over G star to ln 1 plus B psi by B psi, this type of conversion can be safely done if B psi values are small, let us say smaller than 0.2 or even 0.1 to be exact. But for any larger values, we must seek alternative forms. We must seek numerical solution, but there is a shortcut method, and I will present that to you very shortly. Now, that was for m equal to 0 and therefore, u infinity constant. What about if arbitrary variation of u infinity is there, what would happen? Then the Stanton number based on mass transfer, Stanton number as you know is Nusselt number divided by Reynolds Prandtl. Stanton number for mass transfer will be Sherwood number divided by Reynolds number into Schmidt number, and that would equal rho u infinity x by mu. This is Reynolds x, this is x. This will be g x divided by rho m times diffusivity and into Schmidt number, which is nu times diffusivity. So, you can see that the resultant thing will be g divided by rho m u infinity. That is the mass transfer Stanton number. And Spalding and Chi have calculated this problem for arbitrary free stream variations, and you will recall this formula which we had developed for the case of arbitrary variation of u infinity using integral solutions. And the same thing has been done for mass transfer by Spalding and Chi for 3 values of Schmidt number 0.75 greater than 5. In each case B psi equal to 0 of course means no mass transfer, B psi equal to minus 0.9, B psi equal to plus 9 and so on and so forth, and the K1, K2, K3 are given here. These are simply to be used if needed for calculating the mass transfer coefficient G, but the B values must be converted to B psi first, as we demonstrated in the previous slide. Now, let us turn to the turbulent boundary layers. Now, in turbulent boundary layers, we have gamma effective equal to gamma laminar plus gamma T, and gamma T is much greater than gamma L. And we have mu effective equal to mu L plus mu T, and mu T is much greater than mu L, as we have noticed, almost of the order 100 in most problems of turbulent flow. And therefore, the analogy between momentum and heat and mass transfers actually holds very well for much better in fact for turbulent boundary layers. The turbulent heat transfer correlations for V w equal to 0 take the form of Stanton x, V w equal to 0 equal to C Reynolds x to the power of minus m and Prandtl to the minus n. This you remember. Then from analogy, Stanton x V w equal to 0 would be G star over rho u infinity equal to C R E x to the power of minus m and Schmidt number to the power of minus n. And G over rho u infinity therefore, will be G star rho u infinity into ln 1 plus B psi by B psi, and G star would be simply a heat transfer coefficient at V w equal to 0 divided by C p m into Prandtl divided by Schmidt raised to minus m. So, you can see now how we can calculate, and Schmidt is nothing but mu by gamma psi. So, we can actually get the effective value of G star. If Prandtl number was equal to Schmidt number, then of course, G star would be exactly equal to h of V w equal to 0 by C p m, and Prandtl equal to Schmidt essentially means Lewis number equal to 0. And this part of the result we had already shown in an earlier lecture. So, what this shows is that in turbulent boundary layers you must account for Prandtl number and Schmidt number effects to the power of minus n. Of course, in gases Prandtl and Schmidt are very, very close, but in other cases they may be different. So, this is the way one obtains G star in a turbulent boundary layer from a correlation. So, deviations from G over G star equal to ln 1 plus B divided by B at large B w mainly occur due to variations through the boundary layer. In order to appreciate that, let us see what is B psi. B psi, as you will recall, is psi value in the infinity state minus psi value in the wall state divided by psi value in the wall state minus psi value in the t state. So, if I have this as w w, this as infinity state and this as t state, then a large B psi means that psi infinity minus psi w is very, very large. In other words, this value and this value are separated significantly in the considered phase, and therefore, it is quite in effect you can get a profile like that with the value of psi w here and value of psi infinity there. So, if these values are widely separated, it is quite likely that there would be property variations in the considered phase. So, the reason why G over G star is not equal to ln 1 plus B divided by B is simply because this relation was developed for constant property solutions, as we saw earlier, and therefore, it only applies to very small mass transfer rates. But the moment B becomes very large, you must account for property variations. Now, in order to avoid this solution of the complete set of boundary layer equations, here is a advice. In laminar boundary layers, one could easily write G over G star equal to ln 1 plus B w by B psi multiplied by molecular weight of the mixture in the W state divided by molecular weight of the mixture in the infinity state raised to 0.66. This is from this correction is derived from numerical solution of the complete differential equations for large B and allowing for molecular property variations. So, there is no need now again to solve the differential equations. We can simply take this as a correction for laminar boundaries. Likewise, in the turbulent boundary layer, the recommended property correction is same thing, m w over n divided by m infinity raised to 0.4. Now, these relations, these sort of corrections that we have indicated also apply to internal flows. The only difference is instead of psi infinity divided by psi w, so in internal flows, instead of psi infinity, we simply take B equal to psi of the bulk value minus psi wall divided by psi wall minus psi t. So, that is the only difference quite analogous to what we do in heat transfer, where we define heat transfer based on the bulk value and wall value in internal flows, whereas we define it based on infinity and wall value in external boundary layers. So, with that change, you simply interpret B psi equal to psi b minus psi wall divided by psi wall minus psi t, and psi b is the bulk value calculated as usual from integration of the axial velocity profile and psi profile. Now, in order to help computations, what I have done here is to give you the values of binary diffusion coefficient DAB, so that you can evaluate Schmidt numbers and other quantities for any problem that we shall be encountering in the subsequent lectures. So, for example, DAB is the diffusion coefficient. It is always defined for a pair of gases A and B. So, here I am defining it for example, water vapor and air, 24 into 10 raised to minus 6, CO in air 19 into 10 raised to minus 6, and so on and so forth. So, this is for your ready reference which you can use. The only thing to remember though is that these values are at temperature of 300 K and 1 atmosphere, but many times we have higher pressure, particularly in combustion problems, and temperature would also be higher, in which case you simply make a correction. So, DAB at any temperature and pressure divided by DAB at 298 and 1 atmosphere is simply T raised to T divided by 298 raised to 1.5 or 3 by 2 rather divided by 1 over P. So, that is how one calculates. So, the higher the pressure, lower is the value of DAB, but DAB is proportional to T to the half. So, and temperature is to be evaluated in Kelvin, that is to be remembered. So, this is just for your ready reference. So, then for overall procedure now for calculating NW will be for all types of mass transfer problems that we encounter, identify first the appropriate conserved property psi, and we have shown how to do this in inert mass transfer with heat transfer, mass transfer with simple chemical reaction, and mass transfer with arbitrary chemical reaction. So, we know how to evaluate psi. Make sure that B psi can be evaluated from psi infinity, psi t and psi w. Now, usually psi infinity and psi t are known, but psi w is usually not known, and therefore, it has to be determined. There are various ways to avoid knowing psi w. For example, psi w can be rendered 0 simply by taking T ref as T w, but many times that is not possible. And then we must select such combinations of psi that the composite variable would not require value of psi w. We will show you in a practical problem of this nature a little later. But many a times psi w needs to be established from iterations, and I have given you already one example of this type, but we will see many more as we go into the next lectures. Then for the mass transfer problem at hand, identify the corresponding heat transfer situation with VW equal to 0, for which the correlation is available, and hence evaluate the value of H cof VW equal to 0. So, as to evaluate G star H is equal to H cof VW equal to 0 divided by CPM, the specific heat of the mixture, and hence then evaluate NW equal to GB, which is equal to G star H Prandtl divided by Schmidt raised to n, which will come from the correlation, itself, because Prandtl raised to n and Schmidt raised to n are identical, because Nusselt x equal to Sherwood x at constant properties, and then allow for variable property correction m w by infinity raised to some power x into ln 1 plus b psi. So, n and x are to be carefully chosen from the correlation itself, and x value only take in laminar flow 0.66 and in turbulent flow 0.4. So, these can be easily calculated. So, that is the overall procedure then for calculating NW using Reynolds flow model. It will require no solution of any differential equation. Only thing is the psi must be carefully chosen, so that B can be calculated, B psi can be calculated, and then an appropriate correlation must be chosen with appropriate values of n and x, again depending on whether it is laminar or turbulent boundary layer. So, then in summary, I would say that we have thus examined the validity of n w equal to g b psi equal to g star ln 1 plus b psi, and g over g star is in fact equal to f b is equal to ln 1 plus b psi by b psi. But this applies only to very small mass transfer rates b psi. When b psi is very small, this relationship we have verified even from by looking at laminar flow data, boundary layer data that we had computed earlier, and also the turbulent flow data. So, this is valid only for very small mass transfer rates and constant properties. It is shown that the deviations from this formula occur when the fluid properties vary significantly in the boundary layer at large b psi, and hence the calculation of n w is corrected as what I showed on the previous slide, where g star h is equal to V w 0 divided by C p m. So, with this we are now ready to demonstrate applications of Stefan, Couette and Reynolds flow models to problems of engineering relevance, and we shall actually calculate numerical problems, in which first we will consider the Stefan flow model for diffusion problems. We will consider Couette flow model to show that this kind of property variation correction based on molecular weights of the infinity and W states is in fact required. And then we shall move to Reynolds flow model and solve several problems, about at least 8 to 10 problems, so that you can appreciate how to apply these methods for calculating practical convective mass transfer problems.